Something strange is happening in the deepest images ever taken of the universe, and this time scientists are not excited. They're uneasy. When the James Webb Space Telescope began transmitting its latest high-resolution infrared observations, researchers expected refinement, not contradiction. They expected clearer galaxies, sharper star formation regions, better measurements. Instead, they found structures that do not fit. Not into existing models, not into known categories, not even into speculative ones. These objects appear massive, gravitationally influential, and yet strangely incomplete. They do not behave like galaxies, they are not black holes, they are not nebulae, and they are definitely not noise. At first, teams assumed data corruption, then calibration error, then processing artifacts. But the same anomalies appeared again and again across different instruments, different wavelengths, different observation windows. At that point, concern replaced curiosity, because when independent data sets agree on something that shouldn't exist, the problem is no longer the telescope, it's our understanding. The anomalies appear as compact regions of intense space-time distortion embedded in otherwise normal cosmic environments. Light passing near them bends more than expected. Nearby objects accelerate subtly, as if influenced by hidden mass. But when scientists calculate how much matter would be required to cause these effects, the numbers don't add up. There isn't enough visible or invisible matter present. Even dark matter models struggle to explain it, which leaves an uncomfortable possibility. These structures may represent a form of gravitational organization we have never seen before, something that produces gravity without behaving like matter. And that is where alarm sets in, because gravity in modern physics does not exist independently. It is a property of mass and energy. Remove those, and gravity should disappear. But Webb's data suggests otherwise. These regions generate structured gravitational influence without any corresponding mass signature. No stars, no dust, no gas, no accretion disks, nothing. And yet, the effect is real, observable, measurable, repeatable. That means one of two things is true. Either our models of gravity are incomplete in a fundamental way, or the universe is capable of forming stable structures made from something other than matter. And both options are deeply unsettling. As scientists began digging deeper, the situation became even more troubling. The anomalies were not isolated. Webb revealed multiple examples across vast cosmic distances, all sharing similar characteristics. Same scale, same gravitational behavior, same absence of conventional matter. This ruled out local flukes or rare astrophysical accidents. Patterns were emerging, and patterns imply rules. The most disturbing detail came from timing analysis. These structures do not remain static. They fluctuate, slowly, subtly, but consistently. Over weeks and months of observation, their gravitational influence strengthens and weakens in rhythmic cycles. Not random noise, not chaotic turbulence, periodic behavior. That immediately raised red flags. In astronomy, periodicity usually means rotation, orbit, or interaction. But these objects are not rotating like galaxies, not orbiting like binaries, and not feeding like black holes, and yet they pulse. That led some researchers to suggest exotic explanations: vacuum energy condensates, space-time solitons, remnants of early universe phase transitions. Others proposed modified gravity effects, where space-time itself can stabilize into persistent geometric formations. None of these ideas are proven. All of them break something fundamental. And that is precisely why scientists are alarmed. Because if even one of these explanations is correct, it means the universe has been hiding an entire class of objects from us. Objects that do not shine, do not absorb, do not emit. Objects that can only be seen through how they distort reality around them.
Webb didn't just detect them because it's powerful. It detected them because it sees in infrared, where subtle gravitational lensing becomes visible against the glow of ancient starlight. Previous telescopes simply couldn't separate the signal from the noise, but Webb can. And now that we know what to look for, researchers are re-examining old data from Hubble, Spitzer, even ground-based observatories. Early results are unsettling. Faint hints of similar distortions appear in archival images overlooked for decades. That means these objects have likely been there all along, watching galaxies form, watching stars ignite, watching planets assemble, and we never noticed them. The universe did not suddenly become strange. We simply became capable of seeing how strange it always was.
The next question is the one no one likes asking, but everyone is thinking. If these structures exist, what do they do? Gravity is not passive. It shapes orbits, drives collisions, controls cosmic evolution. Even small anomalies can have massive long-term consequences, and these are not small. Simulations suggest that over billions of years, objects like these could redirect gas flows, alter star formation rates, and subtly reshape entire galaxies without ever being visible. They would be cosmic sculptors operating in silence. Worse, some models indicate that these anomalies may migrate, slowly drifting through intergalactic space, following gradients in space-time curvature like currents in an ocean. That means they are not fixed landmarks, they are travelers. And while their movement is incredibly slow by human standards, on cosmic timescales it is significant. One of the detected structures appears to be moving relative to background galaxies, not orbiting anything, not being ejected, simply translating through space. That alone violates expectations. Large-scale gravitational features should be anchored by mass, but this one isn't. And then there's the coincidence that truly unsettles researchers. Several anomalies appear aligned along vast filamentary structures of the cosmic web, not randomly scattered, not evenly distributed, preferentially positioned where large-scale structure forms. That suggests interaction, possibly even participation. Are these anomalies shaping the cosmic web, or are they forming within it? No one knows. And that ignorance is dangerous in science because it signals a blind spot, a place where theory has nothing solid to stand on. Some physicists have begun quietly asking whether these objects could represent a stable configuration of spacetime left over from the early universe, a frozen imprint of physical laws that no longer dominate today. If so, they are not just objects, they are fossils. Evidence that the universe once behaved very differently. And if space-time can crystallize under the right conditions, who's to say it couldn't happen again? Perhaps under extreme energy densities, perhaps near supermassive black holes, or perhaps somewhere closer than we'd like.
So why does this matter to us? Because every time humanity has discovered something that fundamentally changes our understanding of physics, it has reshaped our future. Relativity led to nuclear energy. Quantum mechanics led to semiconductors. Understanding gravity differently would not just rewrite textbooks, it would redefine what is possible. But before we get there, scientists need to answer a more urgent question. Are these anomalies stable forever, or can they change suddenly? Webb's most recent observations suggest at least one structure experienced a rapid internal reconfiguration. Its gravitational profile shifted over a timescale of months, not millions of years. That is fast, alarmingly fast. If these objects can reorganize, merge, or decay, then their long-term influence is unpredictable. That uncertainty is why research teams are being cautious with their language. You won't hear panic in official papers. You'll hear words like unexpected, non-standard, requires further investigation. But behind closed doors, there is genuine concern, because physics does not like surprises at this scale. and the universe has just delivered one. JWST was built to extend our vision, not to undermine our foundations. Yet here we are, staring at something that refuses to fit, something that exists in defiance of expectation. And history shows that when nature refuses to fit our models, it is the models that eventually break, not the universe. Whether these anomalies turn out to be harmless curiosities or signs of a deeper cosmic mechanism, one thing is certain. The James Webb Space Telescope has not just shown us new sights, it has exposed new questions, and some of them are deeply unsettling, because the universe we thought we understood may be resting on assumptions that were never truly tested, until now.